One of the strangest things about electricity is that almost everyone thinks they already understand it. They'll say, "Oh yes, electricity. It flows through the wire like water through a pipe. You turn on the switch and the stuff goes rushing along, lights the bulb, heats the toaster, spins the motor." And that picture feels so comfortable, so obvious, that we rarely stop to ask whether it's actually true. After all, if you cut a wire, the light goes out. If you connect it, the light comes on. So something must be flowing, right? But here's the funny part. Imagine I'm standing in a room with a light switch on the wall. I flip the switch and the lamp across the room turns on almost instantly. Now suppose the wire connecting that switch to the lamp is not a few meters long, but a few thousand kilometers long, stretched out across the countryside. I flip the switch here, and the lamp way over there lights up with barely any delay. Now you might say, well, electricity moves very fast. Fine, but what exactly is moving so fast? The electrons. Let's try to picture that. Inside a metal wire, there are electrons everywhere, sort of like people packed into a crowded hallway. If I push on the person at my end, the person at the far end feels something almost immediately. Not because one person ran down the hallway at lightning speed, but because everyone shifted just a tiny bit. That's already a clue that the water in a pipe picture is hiding something important. Here's the paradox that really gets me. If you could somehow watch a single electron inside a copper wire while your lamp is on, you'd see that it's barely crawling along. I mean, really crawling. Depending on the situation, an electron might drift at a speed slower than a snail taking a nap, and yet the effect of electricity, the turning on of the light, the delivery of energy, happens at a significant fraction of the speed of light. So how can something that moves so slowly produce an effect that happens so quickly? That's the big misconception right there. People imagine electricity as a substance, a kind of invisible fluid that rushes through the wire and does useful work when it gets where it's going. But the truth is more subtle, more interesting, and frankly more beautiful than that. Let me tease you with another little puzzle. Suppose I take a simple loop of wire and connect it to a battery. The moment I complete the circuit, the bulb lights up. Now ask yourself a very specific question. Where does the energy that lights the bulb actually travel? Does it move inside the wire, riding along on the electrons like passengers on a train, or does it come from somewhere else? Most people have never even thought to ask that question. They assume the answer must be inside the wire, because that's where the electrons are. But if you follow that idea carefully, it starts to fall apart. If the electrons themselves are moving so slowly, how can they be carrying energy fast enough to power the bulb immediately? Are they sprinting when we're not looking? Or is the energy taking some kind of shortcut? I remember thinking about this when I was younger, staring at a simple circuit diagram in a book. Battery wire bulb. Very neat, very clean. But real wires live in real space. They're surrounded by air or vacuum or whatever happens to be around them. And that space is not empty in the way we usually imagine. Something is happening there too. Here's a thought experiment. Take a long straight wire and connect it to a battery so that a steady current flows. Now sprinkle some tiny test charges around the wire, not touching it, just floating nearby. Those charges will feel forces. They'll start to move. That means something about the space around the wire has changed. Something is reaching out from the wire into the surrounding space. And that something isn't an electron flying out of the metal. It's an electric field. Now we're getting close to the heart of the misunderstanding. Electricity is not primarily about little particles zooming through wires like marbles in a tube. It's about fields, electric fields and magnetic fields. They fill space. They store energy. They move energy. And they can change very, very quickly. When you flip a light switch, what really happens is not that a bunch of electrons at the switch suddenly decide to dash all the way to the lamp. What happens is that the electric field throughout the entire circuit rearranges itself. That rearrangement propagates through space at a speed close to the speed of light. The electrons respond locally, each one nudged just a bit by the field right where it happens to be. So the lamp lights up not because electrons from the switch race across the country to deliver energy, but because the energy was already sitting in the electromagnetic field surrounding the circuit, and the field reorganizes itself almost instantly when you close the switch. This idea feels unsettling. At first, we like to point at things. We like to say, there it is. That's what's doing the work. Fields are slippery. You can't scoop them up with a spoon. You can't see them directly. And yet, they're the real carriers of energy and momentum in electrical systems. If you're feeling a little uncomfortable right now, that's a good sign. It means the simple picture you've been carrying around is starting to crack. And once it cracks, you can peer inside and see a much richer story trying to get out. A A story where the wire is not the highway of electricity, but more like a guide, shaping how invisible structures in space arrange themselves and move. And once you accept that, an entirely new set of questions starts to whisper at you. If the energy is in the field, where exactly is it before the switch is flipped? How does the field know how to rearrange itself? And why does nature choose this strange, indirect method instead of something simpler? Those questions don't have quick, tidy answers. But chasing them turns out to be far more rewarding than memorizing any slogan about electrons flowing like water. Because the deeper you go, the more you realize that electricity is not a thing at all, but a process, a relationship, a dance between charges and fields that fills the space around us, even when we're not paying attention. Now, once you stop insisting that electricity is some kind of mysterious liquid sloshing through wires, you can finally relax and play with the idea the way nature actually presents it. And nature, I promise you, is far more playful than our bad metaphors. Let's start with something you can almost do at home. Take a battery, a wire, and a bulb. Don't even connect the bulb yet. Just imagine the wire lying there, connected to one terminal of the battery but not the other. Is anything happening? Most people would say no, no current, no electricity, end of story. But that's already not quite right. The moment you connect that wire to one terminal, charges inside the wire rearrange themselves. Not much, but enough. An electric field appears in the space around the wire, like a quiet tension waiting to be released. You see, charges are social creatures. Put one somewhere, and the surrounding space immediately knows about it. That knowing is the electric field. It's not a signal sent later. It's simply how the universe keeps its books balanced. If I place a charge here, the field is there, instantly. That field is the thing that tells other charges how they would move if they were allowed to. Now connect the other end of the wire to the battery and complete the circuit. Something dramatic happens, but not in the way people usually imagine. The electrons in the wire don't suddenly line up and sprint forward like Olympic runners. They shuffle. They drift. Each one moves a microscopic distance. But the electric field everywhere along the wire snaps into a new arrangement, almost like a stretched rubber band suddenly finding its proper shape. Here's an analogy that's closer to the truth than the water pipe, though still imperfect. Imagine a long line of billiard balls touching each other, stretched from the battery to the bulb. If you push the ball at one end, the ball at the far end moves almost immediately. Even though none of the balls travel very far, the push travels through the line as a disturbance, not as a single object making the whole journey. Electricity behaves much more like that push than like water flowing down a pipe. But even that analogy misses something essential, because the push in electricity doesn't stay confined inside the wire, it leaks out into space. In fact, it lives in space. Here's a wonderfully strange fact that engineers use every day without necessarily losing sleep over it. The energy that powers your lamp doesn't mainly flow inside the copper wire. It flows through the space around the wire. The wire's job is not to carry energy like a truck carries cargo. Its job is to guide the electric and magnetic fields so that energy flows where you want it to go. If that sounds outrageous, picture this. Suppose you coat a wire with perfect insulation so no charge can escape, then surround it with vacuum. When current flows, the energy still gets from the battery to the bulb. Where is it traveling? Through the vacuum around the wire, carried by the electromagnetic field. The wire merely shapes the field, like riverbanks shape the flow of water, even though the water itself isn't the bank. This helps explain something that has puzzled people for a long time. If you bring a compass near a current carrying wire, the compass needle turns. That tells you there's a magnetic field swirling around the wire. That swirling field isn't a side effect, it's part of the main event. Together with the electric field, it forms a pattern that points from the battery toward the bulb, showing the direction energy is flowing. So electricity is less like water in a pipe and more like a carefully choreographed pattern in space. Charges jiggle here and there, but the real action is in the invisible geometry of fields wrapping around the circuit. You can even see hints of this in everyday life. Ever notice that when you flip a switch, the light comes on even though the electrons in the wire near the bulb were already there before you touched the switch? Nothing had to travel all the way from your finger to the filament. The field changed, and the electrons that were already in place responded. And that realization opens up another curious thought. If the electrons in your house wiring are barely moving, then some of them might have been there for years. The electron that lights your lamp tonight could be the same one that was loitering in the wire when the house was built. It didn't come from the power plant in the way people like to imagine. What came from the power plant was a pattern, a disturbance, a a reshaping of fields that told local electrons how to move. Once you start thinking this way, the wire begins to look less important than the space around it. And that's deeply counterintuitive because we're trained to trust what we can see and touch. Copper feels solid and real. Empty space feels like nothing. But in electricity, empty space is doing most of the heavy lifting. Now, if fields are doing all this work, the next natural question is, what exactly are these fields obeying? How do they know how to arrange themselves? And why do they behave in ways that sometimes seem almost conspiratorial, coordinating distant parts of a circuit without delay? Those questions pull us gently but firmly toward the deeper rules that govern electricity, rules that don't care about our everyday metaphors and are happy to surprise us if we let them. Once you accept that the space around the wire is not just a passive backdrop but an active participant, you're ready for the part that really twists the brain a little. This is where electricity stops being merely surprising and starts being quietly profound. You see, electric fields don't just appear randomly and do whatever they like. They follow rules, very strict rules. And those rules are so tightly woven into the fabric of reality that once you understand them, a lot of strange electrical behavior suddenly feels inevitable. One of the most important ideas is that electric fields don't like loose ends. If you pile up charge in one place, the field must adjust everywhere else to account for it. That adjustment doesn't wait for permission. It happens because it has to. Nature keeps careful track of where charge is and makes sure the field reflects that accounting at every point in space. Now add motion to the story. When charges move, even slowly, they don't just make electric fields. They also create magnetic fields. And here's where things get delightfully tangled. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. It's a kind of mutual encouragement, like two dancers, each pulling the other into motion. This mutual relationship is what allows electromagnetic effects to propagate through space. When you flip a switch, the change in the electric field near the switch creates a changing magnetic field, which creates a changing electric field farther along, and so on. This chain reaction spreads outward at a finite speed, which turns out to be the speed of light. That's not an accident. Light itself is an electromagnetic wave, a self-sustaining ripple of electric and magnetic fields traveling through space. So when your lamp turns on, the news that the circuit is complete travels outward through space as an electromagnetic disturbance. The electrons in the wire don't need to know anything about the battery on the other side of the room. They only need to respond to the local field right where they are. And that local field is updated as part of this grand, coordinated rearrangement. Here's the counterintuitive part that really bothers people at first. The battery does not push electrons through the circuit in the way a pump pushes water. What it does is maintain an electric field configuration. The chemical reactions inside the battery keep charges separated, sustaining a pattern of fields in space. When you connect a circuit, you allow that pattern to extend through the wire and the surrounding space. The energy flows because the field exists and has somewhere to go. If you insist on tracking energy, not particles, everything suddenly becomes simpler. Energy flows continuously through space, guided by the geometry of the fields. The electrons are more like markers, showing you where the field is doing work, rather than careers carrying energy from place to place. This viewpoint also clears up a long-standing puzzle. In alternating current, the electrons slosh back and forth, barely going anywhere at all, and yet enormous amounts of energy are delivered to homes, factories, and cities. If electrons had to physically carry energy from the power station to your toaster, alternating current would be hopelessly inefficient. But because the energy travels in the fields, the electrons can just wiggle in place, passing the disturbance along like people doing a stadium wave. Now consider resistance, another thing that's often misunderstood. People say resistance is what slows down the electrons. That's not wrong, but it's not the main story. Resistance is where the energy carried by the field gets transferred to matter. Inside a resistor or a light bulb filament, the electric field does work on charges, and that work gets converted into heat or light. The field loses energy there. That loss shows up as a voltage drop. From this perspective, a circuit is not a loop of wire with stuff flowing through it. It's a pathway for energy transfer, shaped by materials that either allow fields to pass energy along efficiently or force them to dump energy into vibrations of atoms. The wire itself ideally doesn't consume much energy. It simply helps shape the field so the energy ends up where you want it. And now for a truly strange realization. If you could see the electromagnetic field around a simple circuit, you wouldn't see arrows neatly confined to the wire. You'd see a complex pattern in the surrounding space, with energy flowing from the battery, curving through space, diving into the resistor and disappearing as heat. the wire would look almost like scaffolding for an invisible architecture. This makes electricity feel less like engineering and more like geometry. You're arranging shapes in space, guiding invisible structures that obey precise mathematical rules. And those rules don't care about your intuition. They only care about consistency. At this point, something interesting usually happens. People stop asking, "Where are the electrons going?" and start asking, "Why does the universe work this way at all? Why should changing fields create each other? Why should energy prefer to travel through empty space rather than hugging the metal that seems so solid and real?" Those questions don't belong to electrical engineering anymore. They belong to our attempt to understand reality itself. And once you step into that territory, electricity stops being just a practical tool and starts looking like a window into something much deeper. If you're willing, we can step back now and look at that bigger picture, where electricity is no longer just about lights and wires, but about how the universe communicates with itself. When you finally step back far enough, electricity stops looking like a trick we've learned to exploit and starts looking like one of the ways the universe tells its own story. It's no longer about switches and sockets, or even about fields and equations. It's about how cause and effect are allowed to exist at all. Think about what really happens when you flip a switch. You make a small, local change with your finger. That change doesn't magically know about the lamp, the wire, or the power source all at once. Instead, the universe enforces a rule. Information about that change can only spread so fast. That speed, the speed of light, is not just about light. It's the speed limit for all influence. Electricity respects it, faithfully. And yet, within that limit, everything coordinates beautifully. Fields adjust, energy flows, charges respond, all without any central command issuing instructions. No little messengers running up and down the wire, just local rules applied everywhere, producing a global result that looks purposeful and intelligent. That's worth pausing over. The lamp lights up not because the universe knows you want light, but because the same laws that govern distant stars also govern the copper in your walls. You and the circuit are both playing by the same rules. There's something almost philosophical hiding here. We like to think of empty space as nothing, as a backdrop where real things happen. But electricity teaches us that space is active. It can store energy, it can transmit energy, it can respond to change. In some sense, space is a participant, not a stage. Once you accept that, the distinction between things and nothing begins to blur. A field is not a thing you can hold, but it's not nothing either. It has energy, it has momentum, it can do work. It can even exist on its own as light traveling through the vacuum without any wire at all. That realization should make you a little uneasy in a good way, because it means our everyday categories are not quite right. Matter and space are not separate actors. They're intertwined. Charges create fields, fields act on charges, and the whole dance is constrained by simple, local rules that somehow give rise to the rich, technological world we live in. It also changes how you think about understanding itself. When we say we understand electricity, we don't mean we've reduced it to something simpler or more familiar. There is nothing more familiar than how the universe actually behaves. Understanding means we've found a way to describe the behavior consistently, to predict what will happen, and to stop being surprised by the wrong things. I used to think that if you could just explain electricity clearly enough, it would suddenly feel obvious, like water flowing downhill. But the truth is better than that. Even when you understand electricity, it still feels a little strange. And that strangeness is not a failure of explanation, it's a feature of reality, because at the bottom of it all, electricity is a reminder that the universe doesn't run on pictures we find comfortable. It runs on rules that happen to be elegant, precise, and occasionally counterintuitive. Our job is not to force those rules into metaphors we like, but to let our intuition slowly reshape itself to match how nature actually behaves. And maybe that's the real lesson hidden inside the big misconception about electricity. The problem was never that electricity was mysterious. The problem was that we were too quick to think it wasn't. Once you let go of that urge, you're free to enjoy the deeper wonder. A simple switch on the wall becomes a quiet demonstration of the universe coordinating itself across space and time, obeying rules that are the same everywhere. And in that sense, every time a light turns on, it's not just illumination. It's a small confirmation that reality is stranger, subtler, and far more interesting than our first guesses ever were.